I'm Mickey Porta. On behalf of New Canaan Library, we welcome you to tonight's final program in the Resilience series, which is on our forests and their champion trees. Thanks to all who have been tuning in to Resilience since February. If you missed any one of our resilience programs, Decoding the Weather Machine in April, Fire and Flood in March, or The Secret Life of Trees in February, you can find them on our library's YouTube channel by going to youtube.com/New Canaan Library. So tonight's program is being moderated by Aaron Lefland, who is the very dynamic executive director of the New Canaan Land Trust since 2017. You could say that trees are Aaron's thing. He completed a Master of Forest Science at Yale, where he studied the sustainable management of New England forests and also conducted research on the demographics of hickory species across the Northeast. His background also includes management of a small-scale community forestry program, as well as research examining long-term forest dynamics. Thank you, Aaron, for being here tonight and bringing us this program.
Thanks so much, Mickey, for that warm introduction and for kicking off this evening. Just so folks know, we sort of have two components to our program this evening. The first is going to be an amazing and inspiring lecture by Dr. Andrew Reinman. And we're going to be following that up with the Q&A, as Mickey mentioned. And then we're going to be diving into what we're calling the New Canaan Champion Tree Project, which is a newly launched citizen science project that'll hopefully engage you guys in collecting data about some of the biggest and largest trees in our community, and learning a little bit about more the importance of those trees. And so hopefully tonight's lecture will inspire us to understand why trees in our community are so important. And then you'll be able to have that sort of hands-on experience collecting data about trees in New Canaan. So back to the start of our program, I am so pleased to introduce Dr. Andrew Reinman. Dr. Reinman is an assistant professor at the Graduate Center at the City University of New York. He's an ecologist and a biogeochemist who focuses on plant ecophysiology and the terrestrial carbon cycle. He's particularly interested in understanding the effects of environmental change, such as climate change, urbanization, and land cover change, on the drivers of plant-mediated controls of terrestrial carbon cycling, nitrogen dynamics as a limiting nutrient, and across a continuum of human-disturbed ecosystems. His research draws from multiple disciplines and combines field observations, ecosystem experiments, and laboratory analysis with geographic information systems, remote sensing, and modeling. He currently has projects in forested and human-dominated landscapes throughout the mid-Atlantic and northeastern United States, and we are so pleased to welcome here this evening.
Great, thank you for that introduction. So let me share my screen here. Okay, can you see the screen okay?
Looks good.
All right, great. So today, what I figured I would do is talk a little bit about kind of relationships between our trees, our forests, and our climate at kind of local to global scales, and also put this in the context of the changing landscapes in the part of the world that we live in. And I'll focus a little bit or draw from some of our research that we're doing across Westchester County, a lot of which is very relevant to, well, much of the Northeast, but certainly to Fairfield County in Connecticut. So when I was a master's student, I was studying forestry, trees, I guess like Aaron, that's my thing, but I had a lot of friends that got to study things like lynx and bears and moose, and they would talk about their charismatic megafauna, and I was always really envious about the like big, cute, cuddly creatures that they got to show on their presentations, and all I had was like a couple of trees to show. But then a few years ago, I heard a dendrochronologist colleague of mine talk about trees, and he used the term charismatic megaflora. And ever since I heard that, I've been trying to incorporate it into talks as often as I can, because I guess if there is charismatic megaflora, it's certainly our trees. And I like to show this picture of a sugar maple because I think there's few trees that are more charismatic than the sugar maple, right? They have this beautiful fall foliage. And of course, we know them for their prized syrup that they produce. And so, humans have a long history of a relationship where they rely quite heavily on trees, right? So Native Americans were the ones to first discover the sweet, sugary taste of maple sap and use it to produce sugar. And more recently, we rely pretty heavily on trees and forests for a whole suite of ecosystem services. Many of them, I'm sure you're quite familiar with. So I'm going to walk through a few of those here, and then I'm going to spend most of my talk giving a little bit of an overview of some of the research that I do, and then focus a bit on sort of the important roles, at least that I think are important to think about, where trees are regulating our climate at local scales and at larger global scales. So of course, we are quite familiar with the utility of trees and forests for providing habitat and for increasing biodiversity, for the recreation and aesthetic value, and because they also play a really important role in dampening noise pollution. We can see that a lot now this time of year that we're starting to get leaves that helps to facilitate that important service that they provide. They're also really important in maintaining water flow and air quality, and they do this through a variety of different means. So they can intercept precipitation, which slows the rate at which water is moving across our surface and into waterways. They transpire a whole lot, so they're taking water from the soil and putting it up into the atmosphere. This helps to kind of control rates of stream flow and the amounts of erosion in our waterways. They're really important for climate regulation, and the ways that they do this, one of which we can hear a lot about these days, and that's their role in carbon sequestration. So they're really important in removing carbon dioxide from the atmosphere and storing it in biomass, and this can play an important role in slowing the rate of climate change. But there's two other ways that they do this that are also really important that maybe we don't hear as much about. And one of those roles is evaporative cooling. So that's where they're taking water from the soil and releasing it to the atmosphere through their leaves. It's pretty analogous to the way that when we sweat and a breeze moves across our arm, for example, that cooling sensation that you feel, that's the water evaporating, which consumes heat. We can kind of think of trees and the transpiration that they're doing as sort of being like the sweat glands of the Earth's surface. And this can have a really profound effect on local temperatures, as I'll show you in a little bit. Also, trees, while they're typically a dark green, when we replace them with dark pavement and dark rooftops, what they get replaced with is typically a darker color than the trees that were there. And that darker color absorbs more incoming solar radiation. That term we refer to as albedo. And so having trees in place instead of development reduces the albedo and reduces the amount of incoming solar radiation that gets converted to heat. And then, of course, we're all quite familiar with the important role of trees in producing shade, which can also help to cool things off. So again, carbon sequestration. This is a big way that trees can kind of help to keep our climate cool. This happens really at a global scale. And then, as I mentioned, at a local scale, the thermal regulation really is referring to surface energy dynamics. And this is through, again, the evaporative cooling and the changes in the color of the Earth's surface. But there's also sort of a co-benefit of this cooling at a local scale, and that's in the capacity of trees to reduce energy demand, which then further reduces carbon dioxide emissions to the atmosphere. And so I just want to take a little bit of time to talk about these two aspects of ecosystem services that trees provide. And I'll start with the carbon piece of all of this. So at a global scale, forests and other terrestrial ecosystems offset about 1/3 of all of our carbon dioxide emissions to the atmosphere each year, right? So another way of thinking about this is because of the abundance of trees and other vegetation on the Earth's surface, climate change is now occurring about 1/3 the rate that it would without the important ecosystem services that trees and other vegetation are providing. And really what's driving this is the difference between two really important processes that occur. So if you dig back in your mind to like 7th grade biology or 10th or 11th grade biology, you'll remember that, of course, trees photosynthesize, and to do this, they're removing carbon dioxide from the atmosphere. But at an ecosystem scale, ecosystems, just like humans, are consuming energy, and in the process, they're metabolizing it and releasing carbon dioxide back to the atmosphere. And so it's this small difference between carbon dioxide being removed from the atmosphere through photosynthesis and getting released back to the atmosphere through respiration. That small difference is the amount that gets sequestered in the forest. And this is important because both of these processes are really sensitive to environmental conditions, things like temperature, light availability, precipitation. And so a lot of the research that I do is really focused on trying to understand how a whole suite of different human-induced environmental changes might alter tree growth and overall rates of forest carbon sequestration. Another question that I try to answer in my research is how might we be able to use trees to further mitigate climate change? And so to think about how these processes pan out in sort of our urban, suburban, ex-urban landscapes, it's really important to think about, well, what's the history of how ecologists have gone to study carbon sequestration in forests? And so for 100 years now, it's been landscapes that look like these that ecologists have flocked to understand all things about forests, right? Like for me, I became a forest ecologist because I like being out in the wilderness. I like studying trees. I like understanding how everything is functioning. And so because of sort of this bias towards these sorts of landscapes, a lot of our understanding of how forests sequester carbon, how they respond to climate and things along those lines stems from research in these landscapes. The potential problem is that more and more of our landscape is looking like these places on the lower left here. And so, for example, while we know that when you take a forested area and clear it, in this case, let's say for a pasture, we know what happens to forest carbon sequestration, right? We lose the forest, we lose that carbon sequestration. But what we haven't spent as much time thinking about is how is this forest fragment that's now left on the landscape, how is it behaving? How is it responding to climate? How is it sequestering carbon? And for a long time, we've made the assumption that a forest is a forest, right? So this large expanse of forest that I'm showing you in these top two images is representative of this little patch here. But as I'll show you, what we're finding is that they are not actually the same thing. They don't behave the same way. If we keep moving in this direction of changing land covers, over time, like through much of our region, we've gone from sort of an agricultural landscape to a now urban, suburban, ex-urban landscape. And we know even less about what carbon sequestration looks like in these sorts of places, right? We know that there's vegetation there, but we generally sort of have ignored it from a carbon sequestration perspective. And so as an example of that, there's a whole lot of different models that scientists use to quantify carbon sequestration at large spatial scales. The map that I'm showing you here is one example. It uses satellite imagery to kind of detect how green the Earth's surface is and uses some other parameters to use that information to quantify rates of carbon sequestration. And you'll notice on this map that there's these big white areas that it just sort of lists as NA. It just assumes nothing's happening there. And these are our, sort of urban, suburban, ex-urban landscapes, where instead of trying to estimate what carbon sequestration looks like, we just sort of make the assumption that nothing's happening there. And in a place like Massachusetts, that can be about 1/3 of the whole state. If we look at sort of the New York City area, we're probably looking at about the same amount or more than that, maybe half of the landscape. But what we're finding is that these areas can be really important, and that's what I want to talk about a little bit. So first, thinking about this from a global perspective, beyond just the greater New York City area that we all live in, some recent work using images collected by satellites has shown that about 1/4 of all of the temperate forests that remain in the world, so the temperate forest, that's an area that sort of goes from sort of the northern half or 2/3 of the US, clear across to Europe and parts of Asia, and some areas of the southern hemisphere. About a quarter of those forests and about 1/5 of the forests in New York State are less than 30 meters from an edge. So this idea of these large intact expanses of forest, like I showed you in that previous image, is really not describing a fairly large chunk of the forest that we encounter. Here's just what sort of New York looks like. The green is all the forest area. The little speckles of yellow are areas of forest that are adjacent to agricultural land. The areas of purple, a lot of which you see here in Westchester, that's areas of forest that are adjacent to developed land. And so you can get a pretty good idea for how fragmented New York's forests are. We can zoom into the Westchester area. I'm sorry that I cut off Connecticut here. It's not because I don't care about Connecticut. It's just because for the purposes of when we made this map, we were thinking about Westchester. So I apologize for that. But you can see how fragmented the forests are. Again, all these purple lines indicate areas of forest that are adjacent to developed land, the yellows adjacent to some sort of agricultural land or some other sort of herbaceous vegetation. Across Connecticut, about a quarter of the forests are within 30 meters of an edge. And the reason why I'm taking so much time here to talk about forest edges is because they experience profoundly different growing conditions than the forest interior. And it's the forest interior that is typically the place that we go to study forest growth, to study forest carbon dynamics. So these forest edges, which again makes up a lot of the landscapes that are around us, are hotter, drier, and windier than interior forest conditions, but they can also get higher access to light and nutrients. Especially in our part of the world, in addition to this forest fragmentation, we have some amount of urbanization and suburbanization to contend with. And we know that urban and suburban areas are also hotter and drier than rural areas. They can often experience greater exposure to pollution and also have greater amounts of nutrient availability because of nitrogen that gets deposited across these landscapes. And so collectively, we can think about forest fragmentation and urbanization as creating this sort of series of risks and opportunities for forest growth and risks and opportunities for the ecosystem services that are provided by trees. So I just want to quickly talk about some of the research that we've been doing in Massachusetts, very similar forest types, very similar landscapes to what we see in Connecticut and New York. So even though this work was conducted in Massachusetts, it bears a whole lot of relevance to the part of the world where we live in. And so what we've been doing is trying to understand how much carbon is being sequestered by our forest fragments, and how does tree growth and forest growth respond to climate? Is it the same as the way an interior forest responds to climate? And is a forest patch or a forest fragment in a rural area performing and acting the same as a forest patch in an urban area? And all of this is really important because if we're really trying to accurately quantify carbon sequestration in our communities, we really need to understand how our forests are functioning in those sorts of contexts. And so what we've been finding is a couple of things. So first, on this graph, what I'm showing you is rates of forest growth in sort of a two-dimensional term that we call the basal area increment, which is just the square meters of wood that a tree puts on each year per hectare. I apologize for all the metric. A square meter is about the same as a square yard. A hectare is about 2.5 acres. Hopefully that helps you to kind of get your bearings a little bit. And when we study this in an urban landscape, we find that as you go from a forest interior, so we find that interior forest conditions in our region is once you get more than 20 meters or so in from the forest, as you go from the interior to the edge, we get about a doubling in the rate of forest growth, meaning we get about a doubling in the rate of carbon being sequestered in trees each year. Here's just sort of a bird's eye view of what the forest interior versus the edge looks like. And so again, there's a whole lot more carbon dioxide being taken up by our forests closer to an edge compared to the interior. But what we also find is that there's a difference in climate sensitivity between the edge and the interior. So on the bottom here on the x-axis, I'm showing you the number of days where the forest is experiencing heat stress. Our threshold in this case is 27 degrees Celsius, which is in the low 80s. This is about the average high temperature in July in this part of the world. And so that seems to be a pretty sensitive threshold for these forests. And what we find is that as the number of days above that threshold increase, rates of forest growth decline, whether you're in the forest interior or the edge, but rate of forest growth declines about 3 times faster near the edge than it does in the interior. So on one hand, these forest patches are growing faster than an intact forest, but on the other hand, they seem to be more sensitive to climate and maybe more vulnerable to climate change than an intact forest. The other thing that we're finding that's really interesting is that when we compare these same types of forests between an urban and rural landscape, while on one hand, we still find about a doubling in the rate of forest growth between the interior and the edge, we find that sensitivity to climate isn't quite as strong. In fact, our interior forests in rural landscapes don't exhibit that same sensitivity to heat that our urban forests do. And by urban here, these are really suburban forests sort of surrounding the Boston area. And while we do get greater sensitivity to heat closer to the edge, it's the magnitude of that decline in forest growth in response to heat is quite a bit lower than it is in our urban forests. And so all of this work is really highlighting that there are these important synergies between fragmentation and urbanization that can exacerbate the sensitivity of our forests to heat. And if we don't take this into account, we might be misrepresenting how these forests are functioning now and how we might expect them to continue to function from a carbon sequestration perspective moving forward in time. And then just to give you kind of a little bit of some context here of what this might mean at a larger landscape scale, I'm going to show you 2 examples from Massachusetts. So in a rural part of the state where we don't have a whole lot of fragmentation and the sensitivity to heat is not quite as high, what we find is that the importance of increases in growth and increases in climate sensitivity are fairly low. But in an urban landscape like Boston, where almost all of the forest is being influenced by these edge effects, that has a profound impact on our interpretation of what these forests are doing from a carbon sequestration perspective. And what we find is that forests in our cities and also in our fragmented landscapes are considerably more productive per unit area of forest than rural forests or than large intact forests. But at the same time, our urban or suburban forests are also likely to be more negatively impacted by climate change because they're more sensitive to heat. So the other thing that is important to think about is not just thinking about the world as forest or non-forest. There's a little bit of a gray area, and I want to get into that now. So if we look at New York, and you can see what Connecticut looks like here, here's a map of different land covers across the region. The different pinks and reds, those are developed land covers. The different shades of green are different forest types. The yellow is some sort of agriculture. Brown is also a form of agriculture. So New York State, for example, is about 65% forested, and about a quarter of the land is active agriculture or some sort of like old field, maybe abandoned agriculture. About 10% of the state is developed, but if we look at the amount of canopy cover that's there, what we find is, so here's what the state looks like with canopy cover. Here's what it looks like just if we separate things out by forest cover versus other land cover types. You can see it's a lot greener when we take into account trees that aren't in forests. When we zoom in to sort of the lower Hudson Valley and adjacent areas of Connecticut, here's, again, you can see the heavily developed landscape. But when we overlay trees that aren't in forested areas, we see it's a lot greener than the way we might sort of intuit just from what the land cover types are. And across New York State, these trees outside of our forests, so really the trees in our yards and along our streets, add an additional 0.3 million hectares. So about another 700,000 acres of tree canopy cover across New York State. Of course, New York's a lot larger than Connecticut, but that magnitude of increase is likely very similar in Connecticut as it is in New York. So it's really important to not just think about forests as the only place where there's important canopy cover, right? The trees that we put in our communities play a really important role. But again, the trees in our communities, we don't think about them very much from a carbon sequestration perspective. So here's an example of a subdivision in a suburban area, and you can see, okay, I'm masking out the developed area and leaving behind just what forest is, right? And so normally we'd make the assumption there's no carbon sequestration going on here. This is the same as what I showed you in the map earlier of what carbon sequestration looks like in these developed landscapes. We assume it's nothing. We've done some work across Massachusetts that it sort of looks at the balance between carbon emissions to the atmosphere from land cover change relative to carbon sequestration by the forests that remain on the landscape. And here's just some examples from the state as a whole, a rural county in the Berkshires and a suburban county near Boston. These flux numbers, the important thing to take home from here is that anything above 0 represents a source of carbon dioxide from the atmosphere, and that's from land cover change. That's what LCC stands for. Really what drives this is when we clear a piece of land for development, the wood that we remove typically gets chipped or burned, and in both cases, the carbon that was in that wood gets converted to CO2 and put back into the atmosphere fairly quickly. Anything below 0 represents carbon being removed from the atmosphere by our forest. That's our carbon sequestration. This would be our typical way of thinking about this. We would assume that, okay, what's considered forest has been lost, and so has all of the carbon sequestration associated with it. But when we look at this area, you can see, well, it's not devoid of vegetation. In fact, there can still be a lot of trees here. And so we've been doing some work to try and understand, well, how fast are these trees growing? How much carbon are they sequestering? And what we find is that the street trees, the trees in our sort of urban and developed landscapes, in our yards, in our communities, grow about, on average, about twice as fast as a forest tree. Here's another example from just street trees, where for almost every size class, this is diameter, breast height, almost every size class of tree, the street tree is growing considerably faster than its same size tree in a forest. So kind of taken together, what this all suggests is that while there's fewer trees in our communities that we've developed, the individual trees can grow substantially faster and maybe have the potential to offset some of the carbon sequestration that was lost when that land got developed. The important caveat here is that while street trees in particular can grow really fast when they're young, they also tend to die young. And I sort of liken street trees to kind of like the rock stars of the tree world. They just sort of live fast and die young. And so when we think about how to manage the trees in our communities, we want to figure out ways to keep this early death, this premature death from happening, so that we can maximize that faster growth for a longer period of time. So now if I come back to this example here, if we now take into account the carbon sequestration that's likely happening by these trees in our yards, along our streets, we find that those trees are now capable of offsetting emissions from land cover change, emissions from deforestation. And of course, this is certainly an upper bound for the capacity of these trees to sequester carbon, but it is important to highlight the real capacity that the trees that we plant in our communities, the real capacity that they have for offsetting some of the carbon sequestration that was lost when we developed that landscape to begin with. So the next piece that I want to touch upon is sort of the way, the utility of trees in cooling things off. And to jump into that, it's important to just provide a brief overview of what the urban heat island effect is. We use the word urban here, but really we can think of it as urban, suburban, exurban. It can happen as scales as small as your driveway. It doesn't have to be a place like Manhattan for it to manifest itself. But what it refers to is the fact that our more developed areas tend to be quite a bit hotter than our surrounding rural areas. This urban heat island effect can exacerbate the intensity of heat waves and the associated public health impacts of these heat events. Also, the hotter conditions that exist in our communities and in our cities, that alone accounts for nearly 10% of electricity demands in the US. And that demand for electricity is to kind of cool our homes and offsetting, the several degree increase in temperature that exists because a landscape has been urbanized. This heat can also exacerbate pollution issues. So things like ground level ozone and smog, the chemical reactions in the atmosphere that produce that form of pollution are accelerated under hot conditions. There's also these really important interactions between the urban heat island effect and climate change. So here's a map showing sort of the spatial distribution of the days that sort of define the threshold of a heat wave in our region. That's days over 90 degrees Fahrenheit. You can see historically, our part of the country has generally experienced fewer than 15 days a year, generally fewer than 10 days a year above that threshold. But by the end of the century, we can expect this to consume a month or more of each year. And so that translates to a summer climate for our region that is more similar to summers of South Carolina. And the other thing is that this increase in warming is going to exacerbate the urban heat island effect, right? And so that warming is going to greatly increase the magnitude of the urban heat island effect where we live. And in our region, it's going to increase it by about 20 or 30%. So there are these important synergies here between this urban heat island effect and climate change that are very likely sort of setting the stage for A, higher energy demands moving forward in time, B, a greater public health crisis, and C, just a reduced level of comfort for us in the summer. So to really understand how we might think about using trees to try and combat some of this, I just want to walk through a quick cartoon that sort of demonstrates why the urban heat island exists. And so really at the foundation of all of this is that the urban heat island is driven by what happens to incoming solar radiation. So this is ultimately the source of all the energy in these systems, with the exception in cities of a small amount of heat that gets produced from internal combustion engines. So if you have your hand near the engine of your car, you can feel heat coming off of it. That's what we're talking about here with our anthropogenic heat. But that's a relatively small contribution. Here's that term albedo again, which refers to the amount of that incoming energy that's reflected back into the atmosphere. You can see there's about 5 times more energy getting just reflected back into the space in our forest system than in an urban system. There's about twice as much energy being dissipated as what we call latent heat flux. That's just the heat that would get consumed by evaporating water, right? So this is transpiration, water getting carried up through the roots and coming out of the tree leaves. That is energy that's not being converted to heat. There's more than twice of that going on in our forest than in our cities. And then the sensible heat, that's the heat that we can feel. There's substantially less of that being produced in our forest than in our cities. And all of this results in 5 times more heat getting stored in the infrastructure, in the ground, in the roads of our cities, compared to the forested landscapes that the cities replaced. This piece, the evapotranspiration piece, winds up being a really, really important component for how trees are regulating climate at these local scales. We can see that visually here. So here's a study site that we have in Maryland. On the left here is just a regular image of what this landscape looks like. On the right is the same landscape, but with a thermal imaging camera, where the warmer colors are hotter temperatures. So you can very clearly see that our forest here are a much, much cooler temperature than even this mowed lawn path here in the foreground, to really get an idea for how important living trees are in cooling things off. Here you can see these red hot branches of a dead tree. Here's that dead tree over here. So it's not just the physical structure of a tree that's cooling things off, it's that physiological process of moving water from the soil to the atmosphere, that sort of like sweating equivalent that trees are doing, that really helps to cool things off. At larger spatial scales, we can see this across New York City. On the left here is a map showing the distribution of canopy cover. You can very clearly see these areas of dark green where all of the parks are. So here's Central Park, here's Prospect Park and Van Cortlandt Park. On the right here, I'm showing you land surface temperature, which is the temperature you would feel if you were to touch the surface. It's not the same as air temperature, but they are correlated with one another. And you can see the areas of blues, those are the cooler temperatures, those all fall where our parks are. So these parks, those vegetated areas, play a really important role in keeping things cool. Just to give you an example of how important this is, especially from a monetary perspective, in the late 2000s, there was a really unfortunate outbreak of the Asian Longhorned beetle in Worcester, Massachusetts. And to deal with this invasive insect, the city had to cut down trees in neighborhoods to quarantine it and keep it from spreading. So here's what that insect looks like. Here's what that neighborhood looked like after they had to cut down all the trees. So again, here's what it looked like before the insect outbreak. Here's what it looked like afterwards. There was this massive decline in canopy cover, and some scientists at UMass decided that they were going to use this as an opportunity to try and understand how this literally or almost literally overnight change in canopy cover would impact energy consumption in these neighborhoods. And so what they found is that prior to having to cut all these trees down, this neighborhood had nearly 40% canopy cover, and during the summer used about 7.1 kilowatt hours of electricity per cooling degree day. In 2009, so the following summer, that nearly 40% canopy cover was reduced to 7.5% canopy cover, and there was a pretty large increase in the amount of energy that was needed for cooling purposes. So there was this 40% increase in consumption for cooling, and the energy that had to be consumed to meet those cooling demands was the equivalent of about 0.7 tons of additional carbon being emitted to the atmosphere each year. And to offset that, they would have had to add 1/3 of a hectare of forest for every sort of hectare of developed land area that exists to offset those carbon emissions. So there's this huge increase in energy demand and an associated large increase in carbon dioxide emissions to the atmosphere. So all that brings us to sort of the last 10 minutes of the talk here, which I hope that information, while maybe a little bit lengthy, provides a nice foundation for why it's important to understand sort of the distribution of our tree canopy and forest resources and how these things are changing over time. And so a few years ago, some colleagues and I got some funding from the New York State Department of Environmental Conservation to conduct sort of an ecosystem service assessment and use Westchester County as sort of a model. The objectives here were to map current and recent changes in land use and land cover, to assess the success of community tree planting programs, highlight forest conservation, afforestation priority areas, and also provide guidance for others to replicate the sort of analysis that we did in Westchester. And really what's most important about all of this is that we set out to do this using only freely available data sets. And the importance of this is that while, of course, Westchester has a lot of resources, we wanted any community to be able to kind of take our protocol and reproduce it for their town, for their county, or whatever. So how do we do this? We do this by relying pretty heavily on satellite imagery. So we have these satellites floating around about 2,000 kilometers above Earth, taking pictures. In this case, the satellite that we're using passes over a particular spot on the Earth every 16 days, snaps a picture, and each one of these pictures has these little tiny pixels that are 30 meters in size, and the color of those pixels can be used to learn a lot about what's on the landscape. It's sort of analogous to if you take a picture on your smartphone and zoom in, eventually it'll look really grainy and pixelated. That's essentially those little pixels is what we kind of take advantage of in these satellite images to understand what's happening at the Earth's surface. Again, this is at a 30-meter spatial resolution, so we break up the whole landscape into these little 30-meter by 30-meter boxes. A meter, again, is about a yard. And we can get all this data freely through a website that's maintained as a partnership from NASA, the USGS, and a few other institutions. They even have this web interface where you can go to the sort of mapping tool that they have and go into any part of the country and zoom in and see the different distributions of land cover. And so we download these data, and in a GIS framework, we can do all sorts of spatial and temporal analyses. So here's what Westchester looks like from a land cover perspective, similar to the maps I showed you earlier. The pinks and reds, those are developed areas. The green is forest. The yellow is some sort of herbaceous cover, typically a pasture, a meadow, or some type of agriculture. The brown is row crops in particular. And as of 2016, which is the most recent data product that's available, they put them out every 5 years. So the 2021 product will probably become available sometime within the next year. As of 2016, Westchester County is about 46% developed, but this development has increased by about 26 square kilometers since 2001. It's about 47% forested, but of course, with an increase in development, we see a decline in forest cover over time. And what you can see from these numbers is essentially all of the new development has occurred at the expense of forest. We can also use this imagery to not just look at land covers, but figure out where there's impervious surfaces like roads and rooftops and sidewalks. About 13% of the entire county is some sort of impervious surface. But we also find that nearly 53% of the county is tree canopy cover. The tree canopy cover has declined by about 20 square kilometers since 2011. So while there's still a fair bit of canopy cover, it's not going in the direction that we want it to. But importantly, more than 10% of all of the tree canopy cover across the county is just from trees in residential areas and developed areas and along our streets. It's not the trees in the forest. So this is another example of how the trees in our communities can play a really important role in boosting the amount of canopy cover. To give you an idea of the sort of like spatial resolution and detail that you can see, I'm zoomed in here to part of central Westchester. Here's White Plains down here. Here's Pleasantville, where I live, up here. And so you can see the high density development in the bright reds here. The center here, we're looking at canopy cover. So those highly developed areas have very little tree canopy cover and a lot of impervious surface. But there's a whole lot of detail that you can get, and you can zoom in really fine. And like I mentioned before, at a 30-meter spatial resolution, figure out what land cover types are, figure out what canopy cover looks like. And also, this is another nice example where this area that is pretty developed can also have a reasonable amount of canopy cover, even though it also has a lot of impervious surfaces, right? So again, these are the trees along our streets and in our yards. The other thing that we can do with these satellites is quantify spatial and temporal variations in temperature. Just like those little thermal infrared guns that everyone gets pointed at their heads now to check your temperature before you go inside someplace, there's like a sort of a glorified version of that on these satellites that is constantly taking the temperature of the surface of the Earth. And we can use this information to look at sort of relationships between canopy cover and land surface temperature. So on the left here, this is the distribution of tree cover across Westchester. The whites and the yellows are areas of lower canopy cover. The darker the green, the higher the canopy cover. So if you're familiar with Westchester much, here's Ward Pound Ridge Reservation, a really beautiful park. Here again is White Plains. And we can get a similar map showing surface temperature. So again, the reds are hotter areas, the blues are cooler areas. Here again is Ward Pound Ridge. It's like this cool little bubble in the northeastern part of the county. If we contrast that to places like Yonkers that have very little canopy cover, you can see how much hotter they are. So the surface temperature is about a 15 to 20 degrees Celsius difference, which is about 30-degree Fahrenheit difference between these two locations that are, it's just a function of canopy cover. And so we can use this sort of data to really quantify the extent to which we can use canopy cover to mitigate the local effects of urban heat island and also help to mitigate some of the impacts of climate change. And also think about how we can use canopy cover and its cooling effects to reduce energy consumption at a local scale. For context, over the past 100 years or so, 150 years, this part of the world has seen about a 1 degree Celsius or 1.7 degree Fahrenheit increase in temperature from climate change. And so these differences in surface temperature, while again is not the same as air temperature, these differences are large and tend to be quite a bit larger than the warming we've seen from climate change alone. The other thing that we can do is look at how different municipalities compare to one another. And when we do that at the municipal scale, what we find is this really strong relationship between tree canopy cover and the land surface temperature. So our communities, our municipalities that have the highest canopy cover are also substantially cooler than the municipalities that have the least amount of canopy cover. The other thing that we're learning is that it's not just that canopy cover cools things off, but there's sort of a temporal signal in what that cooling looks like. And the time of day when canopy cover is most important for cooling things off is sort of the middle of the day and later in the afternoon when temperatures tend to be hottest. So here is the land surface temperature on the y-axis and canopy cover on the x-axis. And you can see it's that middle of the day and the afternoon when we get the biggest difference in temperature between locations that have very little canopy cover and a lot of canopy cover. As a result of that, we can think of forests and trees as kind of creating these more even-keeled communities from a climate perspective. So as we go from low intensity development to high intensity development, you can see that daily amplitude in temperature from the morning to the afternoon increases, while in forest, it's a much more muted change over the course of the day. So those extremes just become a lot less extreme. At a really fine spatial scale, we can also use this sort of information to understand how even small changes in our landscape can have big impacts on temperature. So a year ago or so, I gave a presentation in the village of Pleasantville. And so I'm using Pleasantville as an example here. What this map is showing is changes in surface temperature over this 9-year period, right? And we expect, just year-to-year variations to occur, and so you can kind of ignore the light blues and the light reds. But what we do see is there are a couple of locations where there are these really large increases in temperature, 4 degrees Celsius. That's like 3 or 4 times the amount of warming that's occurred from climate change. On the left here is these two areas being highlighted by these red arrows and what that area looked like in 2011. When we look at what it looked like in 2019, you can see this area had been cleared for a new development of a few houses. And this area that was partially cleared but still had a bunch of trees got converted into a condominium complex with fairly dark roofs. So it doesn't take like Manhattan sort of scale of development to have this effect. It can be as small as just cutting down a small patch of forest and putting up some houses, or putting up an area of condos with dark roofs that can have this important effect. The other thing that we're finding when we're using the data is we can use this to figure out where planting new trees will kind of have the biggest impact. So what I'm showing you in this graph here, each one of these points is a municipality and the relationship between forest cover and canopy cover. So what we're seeing here is as you get away from this blue line, More and more of the canopy cover is being driven by street trees and trees in our yards. And of course, we expect to see that in the municipalities that don't have very much forest. And in particular, it's the municipalities that have very little canopy cover or very little forest cover that have the widest spread have the least amount of forest cover that have widest spread in canopy cover. There's also been some work to suggest that we want to get our communities to be above 40% canopy cover to really maximize the benefits here. So if we think about these areas that are less than 20% forest cover and think about this threshold of 40% canopy cover, what we find is that those areas, even though they have little forest cover, there's a pretty big difference in what the temperature looks like just as you cross that 40% canopy cover threshold. There's also a really important socioeconomic component to this. So our wealthier communities tend to have a lot more canopy cover than our lower income communities. And these are the more stressed communities, tend to be so from both a public health perspective and an economic perspective. And so this sort of highlights maybe where we'd want to focus our efforts for increasing canopy cover. And it's really important, I can't stress this enough, to really think about these feedbacks between socioeconomics and canopy cover and public health. We can quantify changes over time. So here's how temperature is changing over time in Westchester for forested areas and developed areas. They're generally moving in the same direction, though our developed areas are warming a little bit faster than our forested areas. And of course, we see that our declines in forest are essentially mirroring the increases in development, right? So we know that development is happening at the expense of forests. We can also see things like there's this lag between economic activity and land cover change. So 2008 was the housing crisis, but really there was like this delayed impact of development and land cover change that took several years to fully manifest itself before rates of development started to decline. A couple of things just to think about here as I finish up. So what can we do to increase canopy cover? So of course, in our yards, you want to plant trees where you can and make sure that the trees that you're planting are appropriate for the location that you're planting them in. So don't plant a big oak tree or what will become a big oak tree next to a power line. It'll have to get taken down at some point. The other thing that we've been doing with these data is we've been looking at across municipalities, those that have tree ordinances, tree planting programs requiring permits for tree removal, and then seeing how canopy cover in those communities fares over time. And what we find is that, well, of course, everybody's losing canopy cover, but it's really the communities that have tree planting programs that are faring the best. They're still losing canopy cover, but they're losing canopy cover at a much slower rate compared to the communities that don't have these planting programs. So in short, policies and programs matter, and they can make a difference for the trajectory of canopy cover in our communities and the ecosystem services that canopy cover provides. I'll encourage everyone to check out Planting Westchester if you're interested in just learning more about this suite of resources that Westchester County is putting together for what to plant, where to plant it, how to maximize the benefits of canopy cover. The last thing that I'll highlight here, and I know I'm a couple minutes over and I apologize for that, is we can use these data to figure out where forests are most vulnerable. We do this using a combination of where there's land for sale, is it protected land, can the land be subdivided, things like that. And what we come to is, fortunately for Westchester, a little over half of the land is in some sort of protected status, but we still have nearly half of the land that's at a fairly high risk of development because the forest is on land that can be subdivided. I'm going to skip over this, but basically we can use different data products to quantify the amount of carbon being stored in our forests with a fairly high spatial resolution. This is focused on Westchester, it's not super relevant here. Coming back to forest fragmentation, we find in Westchester County, 25% of the forests are being influenced by edges. Because these forest patches grow faster, this means that these forests are sequestering 16,000 tons of carbon more each year than we would have initially thought that they were. This is equivalent to the emissions of about 9,000 cars. I highlight that our patches of forest grow faster and sequester carbon faster than our intact forests, but I want to make sure to throw this disclaimer out because it is not at all a justification for fragmentation as a management strategy. It's bad for biodiversity. You can't fully recover the carbon sequestration that was lost when you deforested part of the landscape to create those fragments. So don't use that as a management strategy. And then I'll just end with some examples of what our data show for New Canaan using these same analyses. So here's a map of your town and the different land cover types. So again, the green is forest, the different reds and pinks are developed. Nearly 60% of the town is forested, nearly 40% is developed, but it has about 62% canopy cover. Although there's been a decline of a little over half a square kilometer of canopy cover since 2011. And then here you can see, similar to what I showed for Westchester, but the spatial variations in temperature and how land cover type influences that, and then also how canopy cover influences that. So again, I'm sorry I went a few minutes over, but I am more than happy to take questions on any of this. So thank you for taking the time to listen to me chat.
Thank you so much, Dr. Reinman. That was incredible, very thorough. I hope folks will take the time to ask questions. If you go ahead and type your questions into the question and answer feature on the bottom of your screen, I'll read out as many of those questions as we'll be able to get through. In the meantime, I'm going to actually share my screen quickly and give a little plug for some of the work that the Land Trust has done on this. Last year, we went through the process of creating a strategic conservation plan and used a lot of the same data sets that Dr. Reinman had talked about, including the impervious surfaces and intact forests and things like that, to create a model for sort of conservation priorities in our community. And that's what this map is here. You can kind of read more through the methodologies and some of the conservation opportunities that we've highlighted in the plan here. But effectively what this map does is it's got different layers showing sort of all these different data sets that we've combined and we created a sort of point system for each of those to identify the areas of highest conservation value. And so some things that kind of stick out are the water company lands at the top of the north side of the town. The land trust parcels are highlighted in yellow here, but there are sort of swaths of high priority areas. Much of that is because there's adjacency to existing land trust properties, but it is something that we're thinking about at the land trust level. And if you're interested in learning about this more, you can just go to our website, About Us, Protecting Open Space, and that'll bring you to this page here. Looks like we've got some questions coming in now. So let's see. Please give the web address for planting Westchester. Dr. Reinman, you'll be able to maybe put that in the chat after or now if no other questions are coming.
Yeah, I'll do it now. I should just mention that it should be live soon, but it's not live yet. So if you don't see the information there right away, just check back again. It's a initiative that's hot off the press that we've been working on for a while and should be ready for prime time before long. So I'll put it in the chat.
Very cool. Maybe we've got a shy audience this evening, which is okay. Well, thank you again, Dr. Reinman. We're thrilled to have had you this evening, and I think unless there's other questions that come in, we're going to transition now into the Champion Tree Project portion of the evening. So for those, actually, I'll just share my screen again. That's probably the easiest way to do this. Is this working? Share, there we go. All right, so back on our website, newcanaanlandtrust.org, up to events and programs, Champion Tree Project. That's the page that we're looking at here. The Champion Tree Project, we initially came up with this idea sort of at the start of the pandemic as a way to get folks out visiting land trust properties or other open space in town. and thought it was an easy way for folks to get outside and do something maybe with their families while socially distanced during the height of the pandemic. And we launched that last year around Arbor Day. And with the Resilience series, this seemed like a great opportunity to sort of relaunch the program and get more folks involved, collect more data, and learn more about the big trees that are here in New Canaan. And so we've developed this webpage. There's a little bit of a background here, but I want to go over basically what the project entails. There's a set system for determining champion trees, and there are, for each species, there are national champions and state champions. And with this project, maybe we'll have some town champions as well. And each tree is given a point value based on its height, its circumference, and the size of its crown spread. And so we thought it'd be fun to identify some of these big trees, while at the same time using that data to collect meaningful information about trees here in New Canaan. And so as Dr. Reinman's presentation highlighted, trees in our community are incredibly important. They provide so many ecosystem services and economic benefits for our community. And so we really want to ensure that we have a good understanding of those sort of specimen trees, those really big trees in our community, so that we can do a better job of protecting them, or working with folks to ensure that they don't get taken down during either development or utility project or something like that. So looking at our website here, we have a detailed instruction sheet. Actually, I guess I'll take a step back. The first thing that we'll talk about is the Citizen Science Kit. So I'm going to stop my screen here. And so thanks to our partnership with the library on this, we have little kits that you'll be able to check out from the New Canaan Library, just like you would check out a book. And within each kit, you'll have a clipboard that has a data sheet for the citizen science program, as well as the instructions that I was just talking about online. The kit also comes with a copy of the Peterson Guide to Eastern Trees to help you identify trees that you might not recognize immediately. It comes with a measuring tape that's going to be used to measure the circumference of the tree. And it comes with a height gauge, which is used to measure the height of the tree. And so the different measurements, those are sort of the measurements you'll take. And on this data sheet, it's laid out pretty simply so that you know exactly what information we're looking for. And so the first one, as I mentioned, is tree species, which we provided you the guide for. The second bit of information we're looking for is the location of your tree. And so ideally, we can use GPS coordinates. If you just drop a pin on your phone when you're in Google Maps or Apple Maps or something like that, you'll be able to get the coordinates of that tree's location. We're going to be doing or measuring the circumference of the tree, and there's some detailed instructions. Sometimes that's a little confusing if a tree has two trunks or is leaning, so there's more information about that. We're going to be measuring the height of the tree. As I mentioned, we've got the angle gauges here. We're going to be measuring what's called the quarter average crown spread, which is basically you take two measurements of the crown spread, the average of that, and then a quarter of that. And then together, those measurements are what determine your tree's point value. So going back to the website, toggling back and forth here, sorry. We've got video tutorials. Actually, I'll just start here. We've got the instruction sheet that you'll be able to use. This is sort of a run through of each measurement that you're going to take. We've got some helpful diagrams here. So how you take the circumference measurement of a tree, what happens if the tree's at an angle, what happens if there's two trunks to the tree, how you take the crown spread using the sort of longest crown spread and the cross spread, and other helpful illustrations. And at the bottom of this is a data sheet that I was referencing before with a sample. So that's sort of the first bit that you'll need. Should any of these measurements provide you trouble, we also have a series of tutorial videos that'll go through each of the different things that we're asking you as our citizen scientists to record. And so that includes everything, again, from how to identify the tree, how to locate the tree, how to measure circumference, how to measure height, how to measure crown spread. And it means you get to listen to more of me talking about trees, which is always fun. The next link here is where you'll go to submit your entry and submit your data. It's just a simple Google form, which again, those sort of 5 data points that we've asked you to collect, there'll be a field for each of those. So your contact information, the tree species, the tree location, circumference, height, quarter average crown spread, and then the total points. We also have a way for you to upload photos should you be unsure about your identification. You can take a photo of the tree and the leaves and send that along. And lastly, we have a sort of data dashboard. And so this is still a little bit in the works, and right now there's just dummy data in here. But what we've done is we've effectively linked the data into this spreadsheet, and this will update in real time as people update or as people input data. And so we'll be able to see how many trees have been measured. We'll be able to see the tree with the sort of highest combined score, so what the current leading champion is in town. We'll be able to see some other information too in terms of carbon sequestration for the trees and carbon offsets for the trees. And we're hoping to expand this dashboard a bit as we get more data. But in order for us to get more data, we need your help. So coming back to the main screen here, that's sort of the gist of the Champion Tree Project. I encourage everybody to get out there. It's a lot of fun. You kind of get to pretend that you're a forester for a day. Go out, measure trees. It's a really fun activity to do with your family. You get to learn a little bit about the science behind forest measurement, tree measurement, and why we use certain measurements like circumference. And one of the measurements Dr. Reinman had talked about, the diameter at breast height, we're using circumference as a proxy for that. So yeah, I hope you'll all participate in that program. It should be a lot of fun. You can help us collect a lot of really meaningful data about our trees here in town. And I do see some things coming up in the Q&A. So let's see. First one here is, at what age is the New Canaan Land Trust hiring for protecting forest? I'm not sure what that means. Somebody wants to clarify that. 2 large trees by Elm Street. Unfortunately, I don't know the answers to these sort of specific questions. I'm sorry about that. But if there are any other audience questions, either for Dr. Reinman or for myself about the Champion Tree Project, we're happy to stay on for a minute and answer those questions. But if not, we really hope that you'll participate in the Champion Tree Project. We hope that you'll take the information that you learned tonight, maybe plant a tree on your property, or encourage a neighbor to do so. Advocate for tree protection here in town, either through the land trust or through protecting trees at town parks or town cemeteries or things like that. Let's see. Oh, good question here. What makes a tree eligible for being a champion tree? We are accepting trees as long as they are in New Canaan and alive. That's basically our criteria. And it's important to remember that champion trees are, so there's 3 measurements. It's the combination of height, circumference, and crown spread. But for each, there's a champion of each species. So something like a dogwood, they generally don't grow very large. So a champion dogwood might only have a score of 50 or 60. I'm kind of off the top of my head here, whereas something like an oak or a big sugar maple might have a score of 200-300 possibly. So for each species, you want to make sure that you're measuring the biggest of that species that you think might exist. And so we've got some really neat examples here in town. Let me just pull my screen up one more time. Share, go back to this page. So this is where you can learn a little bit more about champion trees. If you click this link, that'll take you to the list of national champions. This is a database that's maintained by American Forests, and you can go through and sort by species and see what the biggest of a given species is, or even by state. So just for example, here we'll search for any champions that exist in Connecticut. And we actually do have a couple. These are the largest of a given species in the country. So the largest sugar maple in the United States exists in New London. The largest larch exists in Fairfield. They don't disclose the locations. A lot of these are on private property, but it is encouraging that some of these do exist here in our state. If we want to get a little bit more refined, this second link here talks about state champions, and this is called the Connecticut Notable Tree website. And I was actually tooling around with this today, and we can look at New Canaan, and actually there is a co-champion here in New Canaan. So this little icon here indicates Connecticut co-champion status. So there is a co-champion threadleaf maple, and this one they actually do disclose the location of. It's at the Lakeview Cemetery, sort of near the entrance there. So here's the photo of it. Not sure if anybody recognizes this handsome fellow, but those are the sort of the two websites that you can use to see what champion trees currently exist and are on the record. Getting through the questions here. Here's one for Andrew. What should we be doing to minimize heat islands in urban areas? And are there programs in Westchester or New York City to increase canopy cover? And maybe I'll expand that to if you're familiar with anything in Fairfield County.
Yeah, so that's a great question. So generally, I would argue to plant trees where you can, and again, just make sure it's the right tree. Even a tree like a redbud or a flowering dogwood is doing a lot more to cool off the local environment than having lawn there, for example. And so think about what type of tree is most suitable for where you're planting it, and anything will make a difference. Also, painting roofs white or lighter color shingles, things like that can make a huge difference. And in many cases, if there's tends to be more roof area than area to plant trees, that can have an even bigger impact on cooling than planting trees. Planting Westchester initially started, it was initially inspired by the Million Trees Project in New York City, which did do a really good job of increasing canopy cover. We're doing some analyses to see what that looks like now, but that was a pretty massive undertaking. They did actually plant 1 million trees. In Westchester, the county itself doesn't have a whole lot of teeth in terms of what it can tell municipalities to do, but they can increase canopy cover on county-owned land, and they can provide resources to municipalities to help them figure out where, when, and what to plant to increase tree canopy cover, increase vegetation. At sort of the municipal level, like Pleasantville, where I live, they have a 50-50 tree planting program where the municipality will pay for half the cost of a tree to put up in someone's front yard, and they will come and plant it for you. Those sorts of programs seem to be really helpful in reducing declines in canopy cover. I'm sure there's some sort of similar things going on in different municipalities in Connecticut. I just don't know any specific examples off the top of my head. But those are just some examples of what you can do to kind of mitigate urban heat island. But basically, you want more trees, and things that aren't trees, you want them to be lighter in color.
This is sort of a question that comes to mind just given my house. Do solar panels on the roof, I assume that's taking heat that's usually absorbed by a roof and converting it into a different form of energy rather than heat. It's converted to electrical energy. Are solar panels a good way of reducing a heat island effect?
That's a really good question. I don't know how much they will impact the heat island effect. So they are converting a lot of that light energy into electricity instead of heat, but they're not 100% efficient, meaning that they're not able to take all of the solar energy that hits it and convert it to energy. So typically what's going to happen to the light that's hitting a solar panel that's not being converted to electricity, that's going to be converted to heat. Whether or not it's the same amount of heat as your roof in the absence of a solar panel would produce, I'm not entirely sure. But it will greatly reduce carbon dioxide emissions to the atmosphere, right? So it's reducing temperature at a larger spatial scale, even if it's not having a huge impact right at the location of your house.
I don't see any more questions coming in through the Q&A. So with that, I guess we can wrap up. Thank you so much, Dr. Reinman, for taking the time to be with us this evening. I learned a lot. It was great. I mean, so much of this is new, and it's also just to stay up on the current research on what's going on, and to see it applied sort of so close to home is always great for me and the audience. So I really appreciate you taking the time to be with us this evening. And everybody, I hope you enjoyed the presentation and that you'll participate in our Champion Tree Project. Thanks so much.
Great. Thank you. Have a good night, everybody.